Hello and welcome. I am Melly Annamalai, Product Manager with Oracle, and I'm very excited to share with you some new syntax that we have in Oracle Database 23 that will make it easier for you to write some of those queries. So let's get started. The goal of this new SQL syntax is to help you traverse connections in your data easily. Let's take the example is A connected to B. And let's look at these two tables as examples. I have the bank accounts table, which has information about bank accounts, each row representing an account. And I have the bank transfers table, which has information on which bank account transferred money to which bank account. So in the first row, where it says account 1 transferred money to account 672, that's information that's in the bank transfers table. And I want to look at information or data like that to figure out whether 1 is connected to 833. That's bank account 1 being connected to bank account 833. If I were to do this with SQL without this new syntax, I would write some joins and some self-join queries to get at that information. But what if I could model my data a little differently in what is known as a graph, so that I can more intuitively see that 1 is indeed connected to account 831. This is the graph data model where you take the same data and represent it as a graph where you have nodes, also known as vertices, and edges. Nodes are represented by circles and edges by lines or arrows. So you can see here that when you represent your data as a graph, you can more intuitively ask questions such as whether this data entity is connected to this other data entity. And in our implementation, when you create a graph, you are not moving data, you are not materializing data, you're creating a graph view on your data. More on that later. So in the graph data model, we can ask lots of interesting questions based on how data is connected and the patterns you have in your data. For example, you can ask the question, which are the bank accounts connected to account 960 directly? That's the first one. In the second visual I have here, we can ask the question, which are the bank accounts indirectly connected to account 960? These are the types of queries where graphs really shine, because you can find and traverse indirect connections, not just the direct connections. And in the last visual here, we're asking the question, what are all the paths or all the connections between 1 and 8 and 960? There are several connections. I've highlighted a few of them. So the graph data model makes it easy for you to write such queries. And here's an example of how you can do that with the new SQL syntax you see on the left. I've generalized the query that we were looking at to say, I want to find out whether a bank account represented by source is connected to a bank account represented by destination in 1 to 3 steps. Like bank account 1 connected to bank account 672 is 1 step, and so on. So I want to find out all bank accounts connected to other bank accounts in 1 to 3 steps. If I were to do this in SQL without this new syntax, it would take me like maybe something like 12 joins and union alls to write this query. You can see here that the new SQL syntax that I'm pointing to with this arrow makes it really easy to write such queries. To write such queries which identify how your data is connected, whether there are paths between data entities, and so on. So I mentioned that to use this new syntax, you would need to have a graph representation of your data. And for that, we create the graph view. So in Oracle, when you create a graph view, you're creating a graph representation of your data without materializing the data. So going back to this example that we're looking at here, so we have account 1 connected to account 672. So that's an edge between those two accounts. You have account 2 connected to 833. That's another edge connecting those accounts, and so on. So here is the syntax that is in the standard that was published recently, the new SQL standard, that we can use to create this graph view of data. So I have here the graph name, bank graph. Then I have the table that contains the vertex or node data. So the bank accounts contain the entities and the data that you're looking at. So that's a bank account. So each row in that table becomes a vertex or node in your graph. And then the properties for that node come from the column values. So every node and edge in your graph can have properties, and the properties come from the column values for the nodes and the edges. So we've identified that as the vertex table, and then we identify the edge table containing the information of how data is connected. And once again, the column values become properties. And then you can see here in the syntax, you have the source key and the destination key that links back to the bank accounts table. So you're capturing information about how this data is connected in this graph view. And here is another example of how we would create a graph view of data. Here we have two tables, products at the bottom and product categories at the top. Products belong to different categories. And what is interesting is different categories also belong to a parent category. You might recognize this as coming from the order sample schema that has been in Oracle database forever. So the fact that a category belongs to a parent category creates a hierarchical relationship. And navigating this hierarchy is easy to do with graphs. So if I create a graph from this, I have the products vertex type, the product categories vertex type, and I'm capturing the information that a product is connected to a category and a category is connected to itself through the parent category information. So these kinds of hierarchical relationships can be traversed easily with this graph query syntax. And here I'm asking the question, find me all the products that belong to all the subcategories of a category. And you can see that navigating this kind of a hierarchical relationship is really easy with this new SQL syntax. So all of this has been made possible because of a new standard as part of SQL 2023, published last year. Oracle and various other vendors participated in the standard in the committee to create the standard. And the standard includes syntax for creating a graph that we just saw, dropping a graph, and also syntax for query operations. So I want to reinforce again that in Oracle's implementation of the standard, there is no data copy. Graph is like a view on relational tables. So you don't move your data anywhere. You don't materialize your data. The data remains in place. So any insert, update, delete operations by other business processes are instantly available to the graph. There are no synchronization problems. You update your data, the data is instantly available in your graph view. So that makes graphs work very well with applications that have fast, concurrent update from thousands of users and make our implementation very well suited for operational workloads. And because graphs are a native object of Oracle database in Oracle Database 23, all the other database features apply. High degree of concurrence, you can have thousands or millions of users running thousands of queries. Transactional consistency, high availability. You don't have to worry about having a separate set of processes for your graph database. You can integrate your graph queries and graph data with JSON and other types in the database and so on. So all the features you know and love in Oracle database are available to graphs. And of course, security. You can now work with graphs in the most secure database that there is. And performance, we leverage the extreme scalability of the SQL engine. We've also incorporated innovations in the database for making graph queries extremely fast. So on some of our engineered systems, you can see sub-millisecond response times for billions of nodes and edges. And concurrency, like I touched upon, you can have millions of users writing tens of thousands of queries, updating the data, and the data is reflected in the graph. We run the TPCC benchmark, and there's no performance degradation while working with graph queries. So you might have seen in the JSON sessions, for example, of a JSON duality views, and the similar theme extends to graph as well. You can store your data once, and then you can use it as a relational data or as JSON documents or as a graph. So you don't have to decide early on which data format I'm going to use. You store your data once and then represent it or use it in any form that you want. So let's take a closer look at some of the query examples. So you see here the syntax. I have here the match clause. I have, again, the source account. Anything represented in parentheses represents a node or vertex. In our example, it's a bank account. And anything in square brackets represents the edge. So here I'm looking to list all the source accounts that are connected to an account via this relationship of bank transfers. And I have the columns clause that will return the column that I want to return. So looking at something, a slightly more complex query, I am looking at, again, source and destination accounts. This time I'm looking for all source and destination accounts connected by 1 to 3 steps, or in graph terminology, 1 to 3 hops. And this was the query we were looking at earlier as well. So anything in curly braces represents the length of the path that you're searching for, or the length of the connection that you're searching for between two entities. And I have here a query which is a little different. So it starts with a source account, and you can see here that the final vertex in the match clause is also the source account, the same variable. So I'm looking for paths which are 5 steps or 5 hops long that start and end with the same bank account. Needless to say, financial institutions are really interested in finding this kind of pattern because this is anomalous. When they see money moving in a cycle and moving back to the source account, it's something they want to flag and research further. So finding cycles, finding indirect links, these are the kinds of things that are made really easy with this new syntax. So the outputs of these graph queries can be treated as a table. So it makes it easy to combine the results of your graph queries with other relational tables in the database and other data types in the database, facial data, JSON data, and so on. So our goal is to help you use graph syntax for the graph portions of your query and use SQL and relational tables for others, or JSON documents for other things that you want to do with your data. So rather than move data into a separate, siloed, specialized graph database, where you might be able to do graph queries, but not the other operations as well, by leveraging our Converse database features, you can integrate your graph queries with other different types of data and with relational queries. And here's an example of how that could work with JSON. You might have, as one of your columns, a JSON type, and you might want to retrieve. So the entire JSON data object can become one of the properties in your graph, in your bank account. Let's say it can be one of the properties of your bank account. And then when you want to query this graph, you can use a JSON function that's available with the database. So I can just select the name attribute or the credit score attribute that I want to retrieve from this JSON document. I can also, when I created the graph, I could have selected the JSON attributes that I want to select. So if I don't want to include the entire JSON value, entire JSON document in my graph, I can select the JSON attributes that I want to include in my graph as properties. So let's take a look at some customer examples. As some of you may know, graph support has been there since Oracle Database 12. We have robust support in 19, and now we have this new SQL syntax in 23. So we have customers using graphs already, even if they're not yet using the SQL syntax. And on the left is an example of a payment solutions provider that is using graphs to find unusual, anomalous patterns. It's exactly the example I was talking to you about. So in the visual on the left, they have 2 bank accounts and a lot of bank transactions happening between those 2 accounts, but going through a lot of intermediate accounts. So in their business, this is something they want to flag. Like, why are all these intermediate accounts being used to funnel money from one account to another? Maybe it's they're trying to hide something, or maybe just looking to get around maximum transferable limits and so on. The second example is from a banking customer who's using graphs in a different way. They're also using banks for fraud detection, but they're also looking at graphs as a way to identify communities of users. And this brings me to graph algorithms, which I've not talked about yet, because the focus of this session is on the new SQL syntax that's in the standard. But we can also run graph algorithms such as PageRank, Dijkstra shortest path, community detection algorithms, and so on, that help you identify the entities in your graph that are more tightly connected to each other than they are to other nodes in the graph. So this customer is building a graph of customer relationships based on what customers are doing similar things together. Maybe they had lunch together based on the fact that they swiped the credit cards at the same place and so on. Use that information and then create a graph and then identify communities of users within the graph by running community detection algorithms on the graph. And then using that to identify customers who have similar behavioral patterns. Then the third example is from manufacturing. You can have bill of materials modified hierarchically, like we saw in the orders and in the products and categories example. Or in this example, this customer was using a digital thread to link different components across different tables. And then they can do analysis such as what happens if the design of a component is changed, and which are the two components used together frequently, and so on. So they were using both path queries and then running graph algorithms such as clustering algorithms. And last example is an example from telecommunications about how they use graphs to model communications networks and to do things like what happens when there's a failure, what are the repercussions, and then root cause analysis. If you're using graphs to represent resources in, let's say, a cloud data center, and one resource has a failure, it's going to propagate to everything that it's connected to, and you might get service requests from all of them. So rather than responding to all the service requests, you want to quickly do a root cause analysis, get to the source of the issue, and that would be by looking like traversing paths from the nodes that are sending out these service requests, go to the root of this by doing path analysis, and then addressing the problem there. So let's take a look at some of the tools that you can work with when you're working with graphs and with SQL in Oracle database. Any tool that can work with SQL can work with graphs. So SQL Developer that you're familiar with, and here's an example of a query I'm running in SQL Developer. I'm running the same query with this new SQL Developer extension for VS Code that we have. And then I'm going to show you this visualization tool. So graphs are very visual, and looking at connections, looking at how things are connected, something very visual is possible there. So we have a standalone browser-based visualization tool that you can download separately, that you can use to run queries when you're developing your graph application to see how things are connected and so on. We also make this visualization tool available via an Apex plugin, and also as a JavaScript library that you can use to integrate into your own dashboard, into your own application, and so on. And here's another example of a query I'm running in SQL Developer, and here I'm looking for cycles. You can see that the start and the end nodes that I'm looking at have the same variable source, src, and the same query in a new SQL Developer extension for VS Code. And then here's where it looks interesting in the visualization, because you can visualize right away the cycles. So this is a 3-step or 3-hop cycle. You can see here the accounts. You can see here 918 in the middle in purple color. And you can see the 3-hop cycles that start and end in 918. And you can see the visual representation makes it very interesting to look at the same data rather than just a tabular representation. And that's what this tool and the JavaScript library will enable you to do. So now let's look at how graphs work with machine learning and AI. which is taking the world by storm. I talked about algorithms, I talked about PageRank and community detection algorithms. We also have graph machine learning algorithms that are available out of the box that you can invoke with Java or Python APIs. And these are pre-built algorithms, and they run in Graph Server, which is an innovation from Oracle Labs that is available with your Oracle database license. So you can load your graph from your database into Graph Server to run these algorithms. And what do graph machine learning algorithms do for us? So graph machine learning algorithms provide you more information about your entity to provide additional embeddings for a data entity. So you have raw data, you create a graph from it, and then you can use graph ML algorithms to capture things like graph topology, like how is your data connected to other entities, like by centrality algorithms, PageRank algorithms, or graph machine learning algorithms like deep work. You can capture information on how they're connected to other nodes, which node and edge features they're connected to, and how information propagates in a graph. Like how do the neighbors of a node influence a particular node? And that gives you more information coverage that can increase the accuracy of your machine learning algorithms and maybe help reduce your training step. So let's take a look at this graph machine learning algorithm deep work that basically goes through all the paths you can from a particular node and then concatenates the node IDs on the path. That helps you capture the pattern of how this particular node is connected to other nodes. Fraud detection, for example, if you've identified account 918 as being fraudulent, you can look at the specific pattern and you can find similar patterns with other accounts. So they capture how your account is connected, and that embedding can be captured and used for predictions. And GraphWise, based on the GraphSage algorithm, allows you to learn a function. So it's like a graph convolutional neural network, allows you to learn a function by looking at nodes that are one hop away and sampling data from there, and then sampling data from nodes that are two hops away and so on, and then aggregating information across these different layers. Then finally, I'm going to just talk a little bit about graph RAG and LLMs, which is another hot topic these days. So graphs are used to capture connections. They can also be used similarly to capture concepts from a domain and how the concepts are connected to each other. And this is what is known as a knowledge graph. And there are formal rules and formal semantics for this, or you can just use a simple flexible property graph to represent a knowledge graph. So you have information, for example, here that AI/ML has various subtopics: data science, statistical analysis, LLMs, natural language processing. You have the different tools that you can use to work with these different technologies and so on. So you can use this knowledge graph, represent data, and typically with a knowledge graph, you have experts capturing information about a domain and representing that as this graph. And then you can create embeddings from this graph and use that to provide additional, and use that to search, let's say, a vector database to find similar information, and then use that to provide additional context to your LLM. And that's where graphs can help you capture relationships in a domain, information, concepts from a domain, and then help you find additional context for your LLMs. So with that, I come to the key takeaways that the new syntax in Oracle Database 23AI makes it really easy to write queries that traverse connections in data. The graph data model is really interesting and really useful to find new insights by analyzing the structure of how your data is connected. Oracle Database has comprehensive support for graphs, and graphs add value to machine learning algorithms and RAG, and this is a very hot topic of research. We have various resources for you to get started. Our website, Live Lab, the search for graph. We have a YouTube channel. Sign up to get the latest content. We blog both at the Oracle site and on Medium. So please stop by to check us out there. And that brings me to the end of my session. Thank you very much for listening.